Okay, so this class is Thermodynamics 2 and heat transfer. In my opinion, the hardest one in this building. The most difficult one, the most challenging one in this building. You're gonna hate me, after this semester. So we are going to cover 2 senior courses into one, Thermodynamics 2 and heat transfer. Why? I don't know. Some people 20 years ago designed this one. I don't like it, but it takes a lot of time to change it. So we have to stick to it. So we are going to study thermodynamics first for the first 4 weeks. It's gonna be very challenging because Thermodynamics 2 is way harder than Thermodynamics 1. And the remaining time, we are going to study heat transfer, conduction heat transfer, convection heat transfer, and radiation heat transfer. Each can be an individual course. So technically, 4 courses into one at the senior level. What do you think? Yeah. Okay. All right. So office hour is 10:45 to 11:30 on Tuesday, Thursday. If you have a conflict, you can send me an email. I can log on to WebEx if you don't want to see me in person. If you want to see me in person, use that time. Okay. Time and place of class meetings here, but I want to change it to 128. Hot and humid, like my home country, South Korea. Very hot. There are the two textbooks. The first one is the same as EGR456. I think you already have it, right? The second one is, where is it? Oh, this one, the fundamentals of heat and mass transfer. It's like the Bible in this, the field. So if you may want to have it because heat transfer is important. It's everywhere, okay? By the way, some of you got an email from the library that you have an inclusive access or something. It's just one of the options. We are not going to use that inclusive, the whatever it is called. I just requested it because it gives you another option, and also heard that it is cheaper than the physical textbook. If you want to buy a physical textbook, that's fine. Just cancel it and then buy it, the elsewhere, Amazon or something. Yes. Yes, out of the book. And some of you have a question that, can I buy a previous version, previous edition? Yes, you can. Just find a friend, find a rich friend who has the latest edition, because the homework assignments are based on the latest edition. Because that's how, the publishers get money. They change slightly and they make a new edition. But I have to, to stick to one, the latest one, because the previous edition is not going to be, in the market, right? Or I can copy, and I can make a copy and paste from my textbook and then put it on the blackboard. It's going to be extra effort for me. So maybe not. What? Yeah, you can. Yeah, sure. Okay. There will be 3 exams. Each is 30%. The final exam, as you know from my previous lecture, is not comprehensive. Okay? Each exam is 1 hour. You will solve 3 or 4 problems, because in my opinion, each thermodynamics or heat transfer problem takes about 10 to 15 to 20 minutes. So if there are 3 problems, you can expect that each is going to take about 20 minutes. If you see 4 problems, it is going to be about 15 minutes. So each exam is going to be 1 hour exam, has 3 or 4 problems, including the final exam. Some of you may have a question. Usually in other classes, they have a 2-hour final exam or 3-hour final exam or 8 hours, which is totally fine. Meet together and then decide and let me know at least a week in advance before the final exam. Then if you prefer 2-hour exam, I can prepare, the 8 problems. If you want 3-hour exam, I can prepare 12 problems. I can even do like Olympic games, there's something called cross country or something. 8-hour exam, 4 times 8, 32 problems. Totally fine. I can find the place. Okay, but what I heard from past classes, they're all okay with 1-hour exam. Homework assignments is 7%. There will be 1, 2, 3, 4, 5, 6 homeworks. Not sure. If you go to Blackboard, the homework assignments are already there, so you can see how many are there. Okay. I don't accept any physical copy. So let's save 3. Write it somewhere on a Microsoft Word or the piece of paper. You don't have to write the problems. Just write your solution clearly. I can see whether you know how to solve it or not, and upload on Blackboard as a single PDF. Okay? If you don't know how to make a PDF, that's a problem, right? When you go to the field, you need to know how to make a PDF, right? So this is a good time to review. If you don't know, just go to some website called I Love PDF. They will do the things for you. Or you can go to the computer lab. It has each computer has the PDF program. I don't remember the name of that. So you can convert or if you if you don't know how to convert, the simplest way is that copy your the JPG image or something onto your Microsoft Word and then print it as a PDF. Don't upload 1 gigabyte PDF. That takes about 20 minutes to download. There are 25 students here. So if you upload that kind of file, the per problems, it takes like, a day just to download your, homeworks. You can compress it. If you don't know how to compress it, go to ilovepdf.com or something. And then you can, compress it for free. Or you can use one of the computers here. We have a license from, I don't remember. Yeah. You can compress it. Attendance, 3%. I'm not going to count, the check attendance every class. I will wait the judgment day, the one day, which has the lowest attendance. That's the day I'm going to check attendance. Okay, that one day will determine this 3%. Okay, I think that's the best strategy because I can save my time and then no one is going to miss. Right? Any question? I think that's about it. Any question? Oh, late homework, late assignments will be accepted anytime before the final exam. Okay. However, there's a 20% penalty. Okay? 20% out of 7% is pretty small. So if you miss it, don't give up. Submit your homework. Okay. Any question? Any question? Everyone is talking about the active learning these days. So I need people to just interrupt any time because the talking alone it hurts. Okay, hurts me. So I need a participation from you. Yes. Oh yes, sure. I'm going to record every lecture and post on Blackboard. However, as you remember from the last semesters and before, we had some technical difficulties, the day-to-day. So some of them might not be available. So attend all the lectures. Okay. And 3%. You know that 3%. Yes. I will think about that. But the basic rule is that I will find the judgment day. And I see maybe one day or maybe 2 or 3 days. I don't know how many days I'm going to count, to check the attendance. So when you come to classroom, you see nobody and you are the only one, then you should be, yeah, this is my lottery day, right? So you will get 3%, everyone will get, the minus 3%. So that increases your chance to go to, the A, right? Any question? No? Hey, let's study thermodynamics and heat transfer. Thermodynamics first. Some of you may not remember, the concepts of thermodynamics, the first 2 laws of thermodynamics, how to solve closed system problems, open system problems. So we will do a quick review. Okay, so we will solve some problems together from 3 chapters in Thermodynamics 1, Chapter 3, Chapter 4, and Chapter 6. Okay, so we will go over those problems today. And hopefully you can finish everything today or this Thursday. Okay, and we can start Thermodynamics 2. Okay. First, we will remember how to evaluate a property. There are two different. What's going on? Uh-oh. That's weird. So there are 2 different ways to evaluate the property. One is a phase change material such as water or refrigerant, and the other one is, the pure material such as pure solid, pure liquid, or pure gas. And let's talk about how to evaluate a property of phase change material. So there are 5 phase change processes. The first one is compressed liquid, saturated liquid, saturated mixture, saturated vapor, and superheated vapor. If you were in my previous EGR456, I told you that you remember the table problem, right? I told you how important it is. Now, do you see the game, right? So whenever you have a phase change material, which means that a material that changes its phase in an engineering process, usually between liquid and vapor, if you want to evaluate its properties such as temperature, pressure, volume, the internal energy, enthalpy, or entropy, you need to be able to determine its phase change process first, because you have to use different tables for different phase. Okay? And how can we determine whether it is compressed liquid, saturated mixture, vapor, saturated vapor, or superheated vapor? You can use phase diagram. Phase diagram looks like this. This one is T, V diagram, temperature, V, volume, no, specific volume. If you see a capital letter, this big V, that means actual volume. So this one is actual volume. If you see this giant V, whose unit is cubic meters. On the other hand, if you see this lowercase means specific property, meaning is that actual property divided by mass. So if you see this lowercase v, that is specific volume, whose unit is cubic meters per kilogram. So this one is TV diagram. you can make this TV diagram for a fixed pressure. So in this case, pressure is constant at 1 atmospheric pressure. By the way, 1 atmospheric pressure means the pressure at the sea level. The exact value is going to be 101.325 kilopascal. That is 1 atm. At this pressure, if you make TV diagram, the graph looks like this. Compressed liquid, saturated liquid, saturated mixture, saturated vapor, and superheated vapor. So by being able to make this TV diagram, you can find your system and determine its phase change process. Okay? And there's another property diagram, phase diagram, that is PV diagram. This one is PV diagram at 101.325 kilopascal. You can make another phase diagram that is PV diagram. Looks similar to this one, but upside down. So this one is PV diagram. We have compressed liquid, number 1, saturated liquid, number 2, saturated mixture, number 3, saturated vapor, number 4, and superheated vapor, number 5. Okay? So we can use either TV diagram or PV diagram, depending on the property you know. Okay? If you have completely no idea about a system, then you cannot make this one. You need to know at least 1 or 2 properties. For example, if you know we have a water and its temperature is 40 degrees Celsius. So if you know temperature 40 degrees Celsius, then using this temperature, you can make TV diagram. Okay? If you know pressure, let's say 100 kilopascal, you can make TV diagram. So if you know pressure, you can make temperature diagram. If you know temperature, you can make pressure diagram. Okay? Oh. Another thing is that we can also make the temperature diagram with another property. This one is temperature specific volume. You can also make temperature specific internal energy U, or you can also make temperature specific enthalpy H. They all look similar. Okay, so compressed liquid, saturated liquid, saturated mixture, saturated vapor, and superheated vapor. So depending on the property you want to determine, you can make TH diagram, TU diagram, TV diagram, now TS diagram. Okay, so there are 4 different, the temperature diagram you can make if you know pressure. Similarly, if you know temperature, you can also make 4 different pressure diagram. The first one is PV diagram. The second one is TPU diagram, PH diagram, and TS diagram. If you don't remember which one is what, this one is specific volume. U is specific internal energy. H is entropy. S is entropy. Okay? So these are how to make TV and PV diagrams. I'm going a little fast because I assume that you already know, because we went through these 2 phase diagrams in Thermodynamics 1, right? Any question? No? These are some examples of phase diagrams. The first one is TV, T temperature diagrams, and pressure diagrams. You can see another curve right here. This one. This is called saturation line. So when you make TV diagram looks like this, right? So you can make this TV diagram for different pressures. You can make TV diagram for, let's say, 100 kilopascal. You can make TV diagram for 200 kilopascal. You can make TV diagram for 50 kilopascal. You can make many TV diagrams. If you do, and then here we have compressed liquid, saturated liquid, saturated mixture, saturated vapor, and superheated vapor. If you connect every saturated liquid, it becomes saturated liquid line. If you connect all the saturated vapor, it becomes saturated vapor line. Then you will see this curve, and on top it is set critical point. Above this point, water does not exist. You only have supercritical water. Okay. So these are some characteristics of property diagrams. You don't have question. We are going to, the review how to determine a property. So there are 5 different, the phase change process. First one is number 1, compressed liquid and saturated liquid and saturated mixture, saturated vapor, and superheated vapor. You can determine the phase change process of your system by using property diagram. We have practice problems later, so we can see and we can do them together. Once you determine the phase change process, we are going to study how to evaluate each property. The easiest ones first. If it is saturated liquid or saturated vapor, you can go to the property tables and find their properties directly. For example, if you know temperature of your system, if it is saturated liquid, specific volume is here. Specific internal energy is here. Specific enthalpy is here. Specific entropy is here. So you can go to table A2 or A3. For example, if the temperature is 10 degrees Celsius, and you know it is saturated liquid, 10 degrees Celsius, you know it is saturated liquid. These are the property values. So you can find their properties directly from the property table. If you know the temperature, 10 degrees Celsius, specific volume is 1.0004 cubic meters per kilogram. But this value is after multiplying specific volume by 1,000. So you need to divide by 1,000. So 0.00100004 cubic meters per kilogram. If you want to determine the specific internal energy, UF, which is 42 kilojoule per kilogram, if it is specific enthalpy, 42.1, if it is entropy, 0.151. So that's how you find them. What about if you know pressure instead of temperature? Let's say, the pressure value we know is 0.3 bar. By the way, 1 bar is 100 kilopascal, so 0.3 bar means 30 kilopascal. Then this is the specific volume, specific internal energy, specific enthalpy, specific entropy. What if it is saturated vapor? You can do the same. What about if the pressure value is 20 kilopascal? You know the phase change process is saturated vapor. Then specific volume is this one. Specific internal energy is this one. Specific enthalpy is this one. Specific entropy is this one. So you can find their properties directly from a property table if it is saturated liquid or saturated vapor. Okay. What about if it is saturated mixture? Then it's a mixture of liquid and vapor. There are so many different mixtures. The mixture that consists of 10% of liquid and 90% of the vapor, or the 20% of liquid and 80% of vapor, or 50-50, 40-60. So the properties of saturated mixture depends on the ratio between liquid and vapor, right? Then you need to know the ratio. That ratio is called quality X. Quality X is the mass of vapor divided by mass of liquid plus mass of vapor. So it has a value between 0 and 1. This X is going to be between 0 and 1. 0 means there is no vapor, which is saturated mixture, a saturated liquid. 1 means you only have vapor, so that is saturated vapor. X, quality X between 0 and 1, that is mixture. So saturated liquid, quality X is 0. Saturated vapor, quality X is 1. Then, once you know the ratio, how can you determine its property? You can use linear interpolation. This is the equation. Specific volume V is Vf plus quality X times Vg minus Vf. What about specific internal energy U? Uf plus X times Ug minus Uf. If it is enthalpy H, Hf plus X times Hg minus Hf. If it is entropy S, Sf plus X times Sg minus Sf. So you can use these linear interpolation equations to determine its property. Too fast? No, because you already know them, right? You studied them last year, right? With me, no? I think yes, because I'm the only one teaching thermodynamics in the entire campus. So imagine that, I will be gone for sabbatical next year. Then the last one is, not the last one, superheated vapor. There is another property table only for superheated vapor. I don't have to, explain anything because it's pretty straightforward. You can go to table A4. So for example, pressure is 0.006. Let's say the pressure is 0.6 kilopascal and temperature is 120 degrees Celsius. And it is superheated vapor. There's a 6 kilopascal because 1 megapascal is 1000 kilopascal. 120 degrees Celsius is here. So the property values that you want to find are going to be this one, this one, this one, this one. However, the problem of superheated vapor is when the pressure value and temperature values are not directly available in the table. Then what do you want to do? Linear interpolation. Let's say the temperature is 100. Then you can do a linear interpolation between these two numbers. What about pressure is not 6 kilopascal or 35 kilopascal, but 10 kilopascal? Then you have to do a linear interpolation between these two numbers. So depending on temperature and pressure, you have to do a multiple linear interpolation. Okay? So that's for number 5. What about number 1? We study number 1 at last because it's going to be a little complicated. Finding the properties of compressed liquid depending on its pressure value. When pressure is high, so P is high, usually greater than 2.5 megapascal, then you go to a table A5. When pressure is less than this one, so low pressure, then you assume that there is no difference between the properties of saturated liquid and compressed liquid. So if you want to determine specific volume V, it is the same as Vf at the same temperature. If you want to determine specific internal energy U, it's going to be the same as Uf at the same temperature. Hf at the same temperature. So that's how we evaluate the property. And let's solve some practice problems together. So we are going to, solve this table. I'm pretty sure that you remember this one, okay? Let's do it one more time, just to make sure that, that we remember everything that we studied in thermodynamics. So this table means that, you have 2 property values, and you are going to find all the other 3, okay? So the first line, so each row represents a problem. So there are 1, 2, 3, 4, 5 independent problems, okay? So let's look at the first problem. What we know is the temperature is 200 kilopascal, quality X is 0.7. Then the first clue is that quality X is 0.7. The quality X doesn't exist for superheated vapor because quality X is the ratio between saturated liquid and saturated vapor. Superheated vapor is far away from its saturation, so there is no quality X. Compressed liquid is the same. There's no quality X. The quality X exists only for number 2, 3, and 4. And the value is between 0 and 1, so you can see it is saturated mixture. So it is saturated mixture, phase change process number 3. And we know pressure is 200 kilopascal. If you know pressure, what property table you have to use? Pressure table. You know pressure. You use pressure table. If you know temperature, you use temperature table. So let's go find pressure table. The pressure is 200 kilopascal. So where is 200 kilopascal? We have 0.04, 0.06, very small. Oh, only 2? We need to find 200, right? No, because the unit is different. This one is bar. This one is 200 kilopascal. 1 bar is 100 kilopascal. So 200 kilopascal is 2 bar. It's right here. So when pressure value is 2 bar, and we know it is saturated mixture. So saturated mixture means that it is under saturation in thermodynamics in real life. It is boiling, right? So what is the temperature? What is the temperature at 200 kilopascal? The boiling temperature of water at 200 kilopascal in thermodynamics, the saturation temperature of water at the given pressure, which is 120.2. So the second line, the column represents saturation temperature, which means if this is the pressure, this is the boiling temperature, right? What is the atmospheric pressure in Denver, Colorado? Anyone from Denver, Colorado? About 0.8. So what is their boiling temperature? Only 93. So water in Denver, Colorado boils at lower temperature. That's why there's no good restaurant in Denver, Colorado. Because it boils at lower temperature. So let's say that if you want to cook pasta, you need to leave it in the boiling water for, let's say, 10 minutes. If you do the same in Denver, Colorado, it's going to be undercooked. If you leave it longer, it's going to be cooked well. However, the texture is going to be different because all the food preparation is based on assuming that atmospheric pressure is 1 atm, right? So they have to use a pressure cooker. It means that if you do a pressure cooker business there, let's not talk about business, but it has a potential, right? So 120.2 degrees Celsius is the boiling temperature, the saturation temperature when pressure is high. So when you see this kind of high temperature, high boiling temperature, when you use a pressure cooker. I don't know why I said that, but so this is the saturation temperature. So I'm going to write it here, 120.2 degrees Celsius. What is specific enthalpy H? If you know it is saturated mixture, you can use this linear interpolation to determine its property. And what we want to determine? H. So what is the equation? H is HF plus quality X times HG minus HF. So let me write this equation here. H is HF plus quality X times HG minus HF. What is HF? At this pressure. At this pressure, HF is here, so this number. What about HG? HG is here, and this number. So 504.7. 504.7. Quality X, 0.7. HG, 2706.7. Or 27. Oh, minus HF. This one again, 504.7. So you have everything. You can determine H. That's how you determine a property of your system when you have saturated mixture. No question, right? Very straightforward. We did exam 1 in EGR456 just to practice this one, right? The second one, now we have temperature. Now we have temperature, 140 degrees Celsius enthalpy, specific enthalpy, 1800. So what is the first step we need to do if you want to evaluate its pressure, its quality? You need to determine its phase change process. How do we determine it's a phase change process? I already told you, you have to, where are they? You have to make a property diagram. So let's make a property diagram. I told you that there are two different property diagrams. One is P, temperature diagram. The other one is P, pressure diagram. Since we know temperature, you can make pressure diagram. Just for your information, if you want to make temperature diagram, you need to know pressure. If you want to make a pressure diagram, you need to know temperature. And since we know the temperature, 140 degrees Celsius, we can make pressure diagram. Just for your information, temperature diagram looks like this, and pressure diagram looks the upside down of this temperature diagram. So pressure diagram looks like this. What about this horizontal axis? Can be anything. V, U, H, S. So which one? Just randomly select any of them? No, since we know H, it's going to be convenient to select H for this horizontal axis. So it's going to be pH diagram. On this pH diagram, we need to find three reference properties. They are this one, P set, this one, HF, this one, HG. Where can we find these P set, HF, HG? From the one that you know, from this temperature. So if you know temperature, which table you have to use? Temperature. How can you use pressure table if you don't know pressure, right? So let's go to the temperature table, which is right here. Table A2. How do we know whether it is temperature table or pressure table? Based on the first column. This is temperature, so it's a temperature table. So it's an input, these are output. If you know temperature, these are the values, okay? So 140 is what we know, this one. So let's find P set. P set is saturation pressure. So at what pressure this water, to undergo phase change at this temperature, 3.613. But when you look at a pressure value, make sure you know its unit, because there are so many different pressure units. In academia, we use Pascal, but it's too small, so we use kilopascal. In climate weather industry, they use, yes, millimeter Hg, right, using barometer. If you go to, let's not talk about that. We have, so P set is 3.613 bar. 1 bar is 100 kilopascal, so it is 361.3. 361.3 kilopascal. What about HF? Where is HF? HF is here. HG is here. So what is the temperature? 140. So we are going to use only the numbers on this line. And HF here, so this one. HG here, so this one. So I'm going to write this one and this one to complete this pH diagram. 589.13 kilojoule per kilogram. Hg, this one. 2733.9 kilojoule per kilogram. Now, we just completed this pH diagram. On this pH diagram, this line represents compressed liquid. This point represents saturated liquid. This line represents saturated mixture. This point represents saturated vapor. The last one, I don't know. You know that superheat vapor, number 5. Then, now it's time to determine its phase change process. So, when you want to determine a property, usually you have 2 property values available. You use one property to make property diagram. You use the other property to locate your system on this diagram. So here, we used 140 degrees Celsius to make this pH diagram. Now we are going to use the other property we know, 1800, to locate your system. 1800 is the specific enthalpy. Where is the specific enthalpy? This horizontal axis, right? Where is 1800? Oh, greater than this one, less than this one. So somewhere between HF, HG, somewhere between. So what is the phase change process? Saturated mixture. Any question? So we confirm that it is saturated mixture, phase change process number 3. Then what is the pressure value? Oh, we are at here, right? So where is the pressure on this diagram? The vertical axis. So this is your system. What is the pressure value? This one, 361.3. Then what is the quality X? What is the quality X? You go to the summary, the right here. You can use this linear interpolation equation again. This one, H is HF plus X times HG minus HF. So let me write this equation here. H is HF plus X times HG minus HF. What is H? 1800. What is HF? This one. What is HG? This one. What is HF? This one. So we have everything. Can you determine the quality X? Yes, you can, right? We know all the numbers except this one. You have a calculator. You can determine that. Do I know the number? I don't know. Any question about this problem? I presume that it's too easy, so there's no question, right? Is it too fast or too slow? Just right, okay. Okay, then let's go to the next problem. Oh, we spent already 50 minutes. Now we need to hurry up, hurry up. So the next problem, we have 2 more problems, right? Now this time we know pressure. This time we know pressure and quality X. We know quality X again. What does it mean? If you know quality X, it's going to be either saturated liquid, mixture, or vapor. And quality X becomes 0. That means that we have a saturated liquid. So we have phase change process number 2, saturated liquid. We know pressure value, 950. So we can find temperature, that is the saturation temperature at 950 kilopascal. So let's go find it. So if you find 950, then you get saturation temperature and specific enthalpy and everything. However, if you look at this first table, there is no 950. By the way, 950 kilopascal is 9.5 bar. And we don't have 9.5, you only have 9 and 10. So what do? Give up? No, we can do that. No, engineers never give up, right? We fix all the trouble. No, we never give up. We solve a problem. When there's a problem in the Washington D.C., they need to hire engineers rather than politicians, because the engineers solve problems, right? So we don't have 9.5. We are going to solve it by using linear interpolation. 9.5. So if you do a linear interpolation, what is the saturation temperature? Oh, by the way, if you don't remember how to use a linear interpolation, don't worry about that. This is the simplest way to do a linear interpolation, okay? So the left-hand side, we have a pressure. The right-hand side, we have temperature. In the denominator, we use the lower bound and upper bound. We are trying to find temperature value at 9.5. What is the number below this 9.5? Just 9. What is the number above? 10. 9 and 10. We have a 9 bar and 10 bar. Then what is temperature value? At 9 bar, it is 175.4. At 10 bar, it is 179.9. So we are going to write these numbers in the same location on the left-hand side. So at 9, this is the saturation temperature, 175.4. At 10, this is the temperature, 179.9. So once you complete the denominators, now it's time to write the pressure value that of your system, 9.5. So where are you going to write this 9.5? This one or this one? It doesn't matter. You can write on the left or right. Either is okay, as long as you stick to the same location, okay? So if you use this top left corner, I'm going to say this is 9.5. The saturation temperature is going to be the same. The top left corner on the right-hand side, T set. What about the remaining, how can we complete that? We can use the number in the denominator. Here, 10. Here, 179.9. This one goes up. You got promoted. 179.9. Okay, so if you solve it, you get T set at 9.5 bar. So it's going to be approximately 177.7, right? 65? I don't know. You have a calculator. I don't have a calculator. Then what about H? What about H? We have saturated liquid. That means H is HF. So there's a saturated liquid, VF, saturated liquid, UF, saturated liquid, HF. So our specific enthalpy is somewhere down here, but there's no 9.5. So we have to do a linear interpolation between these two numbers. How? Pressure is the same. Now this time we use H. Enthalpy HF. Lower bound, upper bound, and this is the location, top left corner, the unknown HF. What is the lower bound? This one, upper bound, this one. 742.83, 762.81, and the remaining space can be filled by the number below, 762.81. So if you solve it, you get HF. That goes here, approximately 752.82. So that's how you determine H and temperature. Any question? No? The next problem, one more. Complete this table for water, H2O. Now this time we have temperature and pressure, both of them. So if you have a temperature and pressure, what is the phase change process? We don't know. If you want to determine its phase change process, what we have to do? Diagram. There are two different diagrams, temperature diagram and pressure diagram. If you know temperature, you will make pressure diagram. If you know pressure, you make temperature diagram. If you know both, which diagram do you have to use? Or you can use either one. Okay. So in this case, since we have a temperature table, I'm going to use 80 temperature. So 80 degrees Celsius. I can make temperature diagram? No, we just use temperature. So we are going to make pressure diagram. P, PV, PU, PH, PS. Which one? H, because we want to determine H, right? I'm going to make pH diagram. pH diagram always looks like this. So to complete this pH diagram, we need to know P set HF HG. P set HF HG. So where do we find P set HF HG? From this table. 80 degrees Celsius is the temperature we know. So there's 80 degrees Celsius. At 80, this is the pressure. HF here, HG here. So this is the HF HG. 0.4739. However, this is in bar, not the bar you drink, the pressure bar, right? Wasn't funny? Okay. I will do better next time. So it's going to be kilopascal. So you have to multiply by 100, right? So not 0.47, it's going to be 47.39 kilopascal. What about HF, this number? 334.91 kilojoule per kilogram. And the last one, 2643.7 kilojoule per kilogram. On this diagram, where is number 1 through 5? 1, this point, 2, here, 3, 4, and 5. So once you make this pH diagram by using 80 degrees Celsius, now it's time to determine the phase change process. How do you do that? I just used 80 degrees Celsius to make this pressure diagram. Time to look at the other property we know. 500 kilopascal. So let's find 500 kilopascal on this diagram. 500 kilopascal is the pressure value. Where is the pressure? The vertical axis, right? So 500 is less than 47. No, greater than 47. So it should be up here. So 500 should be up here. So the only possible phase change process is going to be what? Number 1, compressed liquid. That's how you determine its phase change process. Number 1. Then, once you know it is compressed liquid, what is the quality X? There's no quality X. It is away from its saturation. How you determine H? Now we need to go back and review the summary that I wrote somewhere. If the pressure is high, then we go to a table. If pressure is not high, we assume that the properties of this compressed liquid is the same as the properties of saturated liquid as long as they have the same temperature. So you're looking at 80 degrees Celsius. Pressure is not that high. It's only 500 kilopascal, which is 0.5 megapascal. So we can, this is our option. So H is HF at the same temperature. H is HF at the same temperature, 80 degrees Celsius. So HF at 80 degrees Celsius. HF at 80 degrees Celsius. This is the number, 334.91. Any question? Just let me know if it is too fast. Okay. This is a review, not the real Thermodynamics 2. Don't get disappointed. This is Thermodynamics 1. Thermodynamics 2 is going to be very challenging. So if you are so disappointed, you can disappoint it only for the first week, while we are reviewing the super easy Thermodynamics 1 that you passed, right? But that's not, Thermo 2 is not that bad. It's not Thermo 3. Is there Thermo 3? No, there's no Thermo 3. So Thermo 2 is like the final boss. If you play Super Mario, when you're jumping and hitting the block is easy, but when you find this giant total, it's not easy. So here we are breaking the blocks, but when next week we're going to find the totals. Okay. So the last problem. Now we have a pressure 1,000 kilopascal. Enthalpy value is given 3,162.2. So what do we do? If you have 1,000 kilopascal and this enthalpy value, what is the phase change process? We have pretty much no idea. So what we are going to do? We need to make a property diagram. How you can make a property diagram? We can use this pressure value. If you know pressure, what kind of diagram you can make? Pressure diagram? No. If you know pressure, you make temperature. If you know temperature, you make pressure diagram, right? So this time we know pressure, so we can make temperature diagram. It can be V, U, A, H, S. Among them, we can choose H. So TH diagram looks like this. To complete this TH diagram, we have three reference properties that we need to find. They are T set, HF, HG. So where can you find T set, HF, HG? From property table. So there is 1,000 kilopascal. So this is the saturation temperature, 179.9. And we have HF, this number, HG, this number. So let me write these two here. HF, this one, 762.81. HG, this one, 2778.1. So we just finish it, this TH diagram, using this 1,000 kilopascal pressure. Now it's time to look at the other property. The H value. Oh, there's Professor Zhang over there. He's also from South Korea. Oh, okay. So I don't know why he called. So now we know H value is over 3,000. So let's find H. The H is this horizontal axis. 3,000 is greater than this number. 3,000 is greater than this number. So our system is on the right-hand side, right? So somewhere far right, if you go find your system, it's going to be 1, 2, 3, 4, 5. So it's going to be 5 superheated vapor. When you have a superheated vapor, what is the quality X? Quality X is the ratio of saturation system, right? Superheated vapor is not under saturation, so there's no quality X. What about temperature? You can go to table A4, superheated vapor table. Our pressure is 1,000 kilopascal, which is 1 megapascal, and 3,162 is, we don't have it, right? So 3,162 is greater than this number. So this one is H, less than this number, right? So 3,162 is between these two numbers. How do you determine temperature? The temperature is going to be between these two numbers. Then how you determine the exact temperature? Linear interpolation, again. So you will do a lot of linear interpolation in this class. Now the question is, do I have to, do a lot of linear interpolation in an exam? No, I will try my best to minimize the number of linear interpolations. However, in your homework assignments, for you to practice linear interpolation, there will be a lot of linear interpolation, okay? So if you do a linear interpolation, since I just did in the previous problem, I'm not going to do that. The number is going to be 350. So that's how you determine a property of a phase change process. Any question? So that's everything about chapter 3. Besides, pure system. So this Thursday, we are going to talk about much simpler theory, which is the ideal gas equal to state. Then we can finish chapter 3. We can move on to chapter 4 and chapter 6. I think we can finish chapter 4 and chapter 6 this Thursday. So next week, we can start the real challenging thermodynamics 2. Any question about today's material? No? Isn't it that hot here, right? It's not. Yeah. Yes. Oh, so which table do we have to use? You can use either. Yeah, either is fine. I just selected 80 degrees Celsius because the table available, on this slide was temperature table. If you have a pressure table, you can go to pressure table.